for this case, when it was more than opt by 3, the greedy algorithm actually gives you optimum. Okay, I didn't prove that it is optimum. All I showed you is 4 by 3 factor approximation, but actually it can give you optimum in that case. But like for me, this is what I wanted to communicate. So now let's try to make a algorithm for the case when, I mean, first of all, we don't have this algorithm what we are talking about, but whatever this is, it requires a step of an algorithm. So it just happened that algorithm, the greedy algorithm, handled this case in itself. We never had to worry about it, right? But now whatever the future algorithm is may not have that opportunity, right? May not be in like, so somehow it needs to be embedded that for this case make your algorithm which is good. You understand my point, right? If such a case arises, your algorithm should have a subroutine, hey, this case has arisen, solve me nicely. You understand? Okay. So first of all, in this thought process, there are several things that we need to worry and we need to care. Okay. So let's try to understand that. I would like, so let's collect some observations first of all. Okay. The greedy algorithm for the case when every item has size strictly greater than opt by 3. Okay. Only then. Okay. So we are trying to make an algorithm. So we need the notion of big job, medium job, small job. Now suppose Pn is if it is less than 1 by 10 opt, then this is great. So now we are going to do for the case when opt by 10. Suppose I wanted to make an approximation of them with factor 1 plus 1 over 10, right? So I fixed epsilon equal to 1 over 10, and then we will see that every idea that I try to communicate to you, it can be done for everything else. So epsilon equal to 1 by 10. Okay. So it is 1 by 10. Now there are several cases. First of all, let's just write it down. These kind of statements I would like to write. So now I am deleting this, and I'm going to give you an explicit algorithm for this case. Okay. So let's first of all write down, if Pn is at least strictly greater than opt by 10, then in opt schedule, then in opt schedule, then in opt schedule, number of jobs that can be assigned to a machine is less than equal to, each job is opt by 10, right? So at most this in the opt schedule, look at the optimum schedule, right? Because it can't, right? So it is 9. So if I would have made greater than equal to, then it would have been 10. Okay, it's just like, doesn't matter. Okay, so that is one thing. Aha. So now we have started to understand. Now also let's, okay, but okay, so okay. Now imagine that I only had, so but now still Pn is at least opt by 10. So look at the jobs, okay, and they have processing time P1, P2, P3, Pn, okay, and each of them is more than opt by 10. This is all that I know, that because Pn is greater than equal to opt by 10, each Pi is greater than equal to opt by 10. Is that fine? Now I also told you, so first of all, each job can be assigned to 10, and this. Let's try to solve this problem in polynomial time, right? At least, or for this, ideally, if we can give 1 plus epsilon approximation, 1 plus 1 by 10 approximation, we are very happy. But let's try to do solve this problem in polynomial time. Let's be brave and see if we can solve the problem in polynomial time, and if we fail, then we'll see what to do. Okay, so let's be brave now. Okay, so I'm being brave. Okay, and suppose for now, okay, so now look at this processing time. I say that I write something more. Different processing times is less than equal to k. Okay, you understand what is the meaning of different processing time? So, for example, there are n processing time, but this could be 2, this could be 2, this is 10, 15. So, I call, oh, they have the same processing time, but this job has different processing time. So, number of processing time, different processing time is upper bounded by k. So, for example, for our case, let's take the different processing time is bounded by 100, for example. Is that fine, right? I mean, all these are very unrealistic experiment, like unrealistic. This is unrealistic. This is not unrealistic. This is a fact, right? This is a fact. Okay. So, different processing time is at most 100 kind, right? So, now I can start to understand each machine. Okay. So, now notice these jobs which is 100, same processing time, they are similar, no? I mean, how does it matter? Like, I mean, there is no preferential order between them. So, if I look at the sorted order or whatever order, they are going to come together. So, I am going to just treat them together, okay? Right? So, ultimately, I ask myself, I look at a machine and I said, I ask following question, okay? So, imagine the different processing time is like T1, T2, Tk, where Tk is 100. These are different processing time, okay? And the way, this is exactly what I'm trying to do, okay? This is exactly what I was trying to do. And how many items of processing time 1 is N1, how many jobs of processing time 2, N2 and Nk, right? So, if you sum them up, this is equal to N, right? So, I'm just saying, okay, oh, how many jobs takes 3 units of time? You say 10 of them. So, N1 is 10. I ask you how many jobs takes 100 units of time. So, you say me, hey, that is like some 73. So, N100 is 73, just like that. Okay. Now, I take a machine and ask myself a question. Some machine, how many jobs, hey, how many jobs of Ti is assigned on you in optimum? This is bad, okay? Assigned in opt, right? Is that fine? I have no idea what those numbers are, right? But I'm asking, hey, machine M, how many jobs of processing time Ti is assigned at you in opt? I have no clue what it is, but it is some number. Now, let me ask. So, given this machine M, I define a vector. What is this? C. Okay. So, the vector C, it stores C1, C2, Ck. And what is it storing? What is Ci? What is Ci? Number of items or jobs, I don't know what, assigned to M of a processing time Ti. Okay? So, Ci could be 0 for all that you care, because maybe there is no process, no guy which has been processed. Do you realize that? Okay? Okay. So, this is it. So, now let us ask ourselves, how many such vectors are there? How many such vectors are there? Let us ask ourselves. C1 can be? Wait. No. What number of jobs that can be assigned to M of type 1? How many jobs can I assign of type 1? No. No. Please. No. At most 10. At most 10, because total number of jobs that I can assign to any machine is 10. So why will you assign to as much as you like? I mean, come on, you have no option.
So CI is number of jobs assigned to M
Of particular type, of processing time Ti. Of processing time Ti. Look, I am trying to solve this problem, right? So C1 can be how much? It could be either one item, one job, two job, three job, for whatever. It cannot be more than 10 jobs here. Is that fine or is that not fine? Because each job is big. Okay. So C1 can take how many numbers? 10 numbers. Oh, you're right. It can be 0 too. Right? So any Ci is element of 0, 1 to 10. Is that fine? So how many such vectors are there? Excellent, 11 to the power k. Very nice. Okay, so there are such 11 to the power k vectors. Okay, okay, and I'm going to say, and look, for now I know what opt is. Okay, I know what opt is. I said, now let me define. I say, a vector C is legal. What should I say? C is legal if summation Ti Ci is less than equal to opt. You understand? Like, I mean, if you put this and the total amount of time is more than plus, this is why it is legal. You should not be assigning to this, because in opt this assignment never happens. This is a legal vector. Okay. So first of all, you take your vectors, delete all illegal vectors. Okay. So now let L is set of legal vectors. Excellent. Now I'm not going to tell you anything. Okay. Okay. I told you for your machines, I have not told you opt. You have not seen opt. Okay. Opt, like how this assignment has happened, I have not told you how jobs are assigned to machines. This I am not telling you, but I tell you the following information. Hey, in your algorithm, 55 vectors of, so how many such legal, 11 to the power k legal vectors are there, right? I told you which all vectors are used and how many times on machines. You understand? So I told you, so imagine that this is 11 to the power k vectors. I told you on my machines, which all vectors are used. Okay. Okay. So first of all, among all these legal vectors, how many of them are there? 11 to the power k are there, right? And I ask myself, which of these vectors are used on my machines in opt? Which of these vectors are? Why, Sushmita? 11 to the power k can be much, much smaller than m, no?
Sure.
Yeah, so.
But for every machine, you pick one vector. That's what you mean, right?
No, I'm not saying that. Which all of these vectors are used on my machines?
Yes. So
This is not the same thing. Let me explain to you. Maybe the same vector is used on 3 machines.
yes, that's okay.
Yeah, so I'm saying from, yeah, fine. So I do not want to do it. From 11 to the power k, I'm asking you, which of these vectors is used in my opt solution? Which of these vectors? In the worst case, is 2 to the power 11k. Right? All possible subsets. So you decide. Okay. So that is which of these vectors are used in this. So that is nothing but some S which is subset of legal vectors. Right? I say, this set S is used on my optimum solution. I can check. Like I will try all, so don't worry about this. So I'm making an FPT of them, don't worry. So S is a subset of L, right? How many such subsets are there? 2 to the power 11 power k, which is fine. Summation of Ci? Yeah, you should put that too. I mean, yeah, you should also. So if you define legal, I mean, you can define, you're right, is less than or equal to 10. Because there may be some vector which may not be even allowed. Some type job may not be even there on that. So that is 0. Imagine that you have 35 jobs of different types. Maybe some job is not even assigned on this machine. So what is its coefficient? 0. That's why there are 11 choices. No, no, no. This is not 11. What is this? All of
Each value of Ci is 11.
yeah.
So 11 in
Huh? Wait. Is 11 power k wrong or right?
no each
Wait, Sushmita, wait. Let me, don't confuse. Okay. So what is he saying? Let me first. Okay. So I'm only talking about 10 length vectors. Okay. So each of these item, it's a k length vector where each of these items can be 11. Doesn't matter, no? How does it matter that is upper bound? Like, but is this upper bound or not? Then let's not worry, no? I thought there's something, no, like you can shrink those things. I'm not even trying at this point of time. Like, that is not what we are, let's focus on, okay? Okay, so I got these vectors. I said, these are the vectors which is used in your opt. It's nothing. So for example, k is like 10, this is a constant. So why are you worried? Okay? But now I'll tell you something interesting. Okay? Okay? Which vectors? Okay, no, this I have anyway written. Okay. Now I also told you that now I gave you S. Now I gave you S, this S. It has some set of vectors that are going to be used. So I said, I don't know how many times they are going to be used. So it is maybe Si in S, or say Sj in S, alpha j times, okay, Sj in S, alpha j equal to m. So this particular vector is used on alpha j machines. So what is alpha j? Number of machines vector Sj is used. That's all I'm asking you. Is that fine? Right? If I told you alpha j's and S, can you solve your problem in polytime? Huh? It doesn't matter. Pick up first machine, assign it with respect to one Sj. How many times? Alpha j. Done. Next, same assignment on that. Because in which order you do, processing time remains the same, no? Machines are ordered in which, like, can the sum be different? First you do this one and then this one, right? So I say, okay. So it basically tells us alpha j machines have, so what is so it says alpha j machines, how many machines? Alpha j number of machines has 5 jobs of type 1, 10 jobs of type 2, or whatever these numbers are. You push them. That's it. I'm done. Okay. What is this number? But I have to do this. What is the solution to this equation? What is this? J in S equal to M, where each alpha j is greater than or equal to 1. Do you remember? It is system of x1, x2, x3, x4, x5 equal to n. How many non-indicative integer solutions are there? No, you don't know. All of you people have created past, jest and this and that, right? You don't know how many non-negative integer solutions x1 to xk equal to n, xi are greater than or equal to 0. How many solutions are there? N plus? Exactly. Excellent. So how many such choices are there? How many such solutions are there?
But the size of S will matter, right? Because that divides them.
Yeah. So what?
That depends.
That is some at most 11 power k, no? How does it matter? For me, that is a constant. This is a constant. I don't care. I don't care. So this will be m plus size of S minus 1, choose S. Is this fine? Which is m power mod S less than equal to. So, this is like m power 11 to the power k. Fine, no? Right? S is like at most 11 power k. Size of S is upper bounded by L, no? So, this is fine. I have solved the problem. Excellent, right? You will say, yeah, this guy is like cheating all the time. Okay. First of all, yes, so I have solved the problem in time. Okay. So, if the different processing time is bounded by k, so how will I solve that? And I know opt. First of all, I know opt. So, what I do? I create these vectors. Okay. First I know how many processing time k, right? This is what I wrote. This is a function of k. So, what I do? I create this set of legal vectors. Okay. Then I choose S. Okay. Then I don't know how many of them are going to be the solution, but there are some constraints to be added. What is the constraints here? Here should I add? There are some more constraints to add, no? All the items needs to be assigned, right? So, you should check all those things also. What is this? This is a solution to this equation, but if I look at any processing type item, some alpha j, if I sum those, it should be equal to the number of items that we are using. You understand? No. No? Okay, so let me show to you what I am writing. So, what did I choose here? I chose what is S, set of legal vectors, right? So, let us write down C1, what is this? C1 0, C1 k. This is my first legal vector. C2, C2 0, C2 k. C F. Right? What it tells? Now, so this is used how many times? So, C1 0 is used how many times? Alpha I times. Okay. So, let us multiply with alpha I times. So, if I write summation alpha I, okay, I going from 1 to S, right? This is alpha I is this, right? And for all j, right, this alpha I, okay, and wait, this. So, I have done this, and C I j should be equal to how much? What is this tells us? This tells us how many items of processing time 0, how many times of processing time this. So, this should not, oh, this is not 0, 1, 1, 1, right. So, that should be equal to the total number of items of this type. So, this should be equal to Nj. Otherwise, how will I use it? So, this also constraint needs to be added, right. So, whatever you found your solution, you should check, does it satisfy this? If it doesn't, this is a bad solution, right, because now we are enumerating all solutions of this, you will also enumerate this.
So shouldn't we add that to the legal definition of legal?
What? No, I can't add this to legal definition. Legal is for one machine, right? How many items of particular type I am using? Okay, but like, do I need to do this? Or all I care about is writing some system of equations, ILP solving. Okay, but forget it, that doesn't matter. But you realize I can enumerate all possible solutions to this equation in this time, and I can check if for any one of them this is true, then I am done, because it basically tells us, what does it tell us? Each of these vectors is legal, great, and how many vectors I have chosen? M of them, and now what is the property? And I have only chosen those whose coordinate wise also there, just put them, you are done, there is nothing to it, right. So, it is all about, does there exist a system solution to this system with the property that this constraint is satisfied, because in itself each of them is legal, so no issue, they all will fit greatly on any of them. All I care about, can I place these things together so that every item is used, and that is what I have guaranteed by choosing these coefficients. Is that fine? Excellent. Okay. So, what is the running time of this algorithm? Running time of this algorithm is m to the power some function of k, right? This is such a bad algorithm. This is such a bad algorithm, no? Right? Because if the number of types, this k, if k could be as bad as n, k could be as bad as n, no? What are we talking about, right? Then it's like, oh, you told me that you are going to make a polynomial time algorithm in this course, and all you are making is some stupid exponential time algorithm. Not accepted. So, we have to first find some trick. So, here is a trick number 1. What is that? So, what all tricks do we need in this? Look, so my setup is all well, right? Everything was all okay except that reduce k. So, what does it mean? I also told you that if k was really constant, then I actually gave you a polynomial time algorithm to solve this problem. If the number of types of the object at this point of time, if the distinct processing time was like 10, what is my running time of the algorithm? Some m to the power function of 10, which is poly time. I am very happy, but unfortunately that cannot be done. Okay? Okay. But I will do it, but at a cost, at a loss. Okay? At a loss. So, now do you at least understand the overall idea where my algorithm is going to do, right? So, I reduce this problem of load scheduling in one case to nothing but trying to find items in a way that like sum is equal to this, like all these kind of things, right? So, I try to understand the problem more like a ILP problem, integer linear programming problem, rather than load scheduling problem. Okay? And how did I capture? I captured that by types of each machine, like a vertex covered types. Okay, so it's basically that type, and yeah, and how many items of each type is what, right? So basically, I can think of each of this type as variables. My ILP, I can actually write an ILP from here. Xi's are like variable, which picks up whether alpha j's are selected or not selected, and something of this nature, right? So I will, rather than writing searching S subset of L, I can write whether a particular vector is selected or not. 0 times, 1 times, 2 times, 3 times, 4 times, 5 times. So let's write it down this first. Okay. So before we go, let's write it down. Let's write it down, this integer linear programming. Okay. ILP. Okay. So basically, if you think whatever I try to do here, what did I try to do? I try to say whether a legal vector V in L is selected, and if yes, how many times? Is that right? That's all, no? That's all that I did, right? Because what does alpha j tells us? When I said greater than or equal to 1, it basically tells us is this. So I could have, rather than selecting S subset of L, I could have said you select Sj in legal vector, but alpha j is greater than or equal to 0. Fine. It means some vectors are not chosen. That's it. You understand? Some vectors, when I allow alpha j equal to 0, it means some vectors in L are not chosen, 0. That's it. Okay. So now what I do, for each vector v in legal, let's have a variable yv. Okay, yv is a variable which will tell you how many times I am going to pick up this vector v. Okay, you understand? Okay, so now my question is, what is this? Okay, so I want to select, what do I want to select? I want to select yv1, okay, yv, let's say this has P, cardinality of L is equal to Q. Okay. So, V1, VQ, I want to select YV1, YVQ in Z or say natural number comma 0, right. I want to select, but some constraints should be satisfied. What are the constraints should be satisfied? Anyway, they all are legal vector. So, they all will fit well on each of them, such that first of all YVI I in Q is equal to M, right. So, this tells us total types that we have chosen, like 53 of this type, 33 of this type, their total is M. Okay, that is one thing. And secondly, I need to have a constraint, that each item is taken. So, what should I write here? Each item. So, for all j in 1 to k, these are the different types of elements, right. For each j in k, what should I say here, right? For each j, so I am talking about the k, so this should be equal to Tj. Okay. So, this is, I said, oh, now what?
Yeah, number of jobs of type J, everything has been picked up.
Yeah. So, how do I write? So, look, so this is what I have to write, right. So, YVI is a vector, right. So, look at this YVI. Okay. So, YVI, I know what Cj is, right, because I know what this vector Vi I know, right. Vector Vi I know, right. So, I am going to write, this is nothing but YVI number of times Vi j tells you this number, huh? No, I have written now vector Vi. So, Vi of j I going from 1 to Q should be equal to Tj. Is that fine? Do you understand what is it? What is this? Look at, huh? Sorry, my bad, Nj. That's it. That's all that it is. Okay. Okay. So, there is a great theorem by, so if I have a system of, if I have a solution to this system of equations, then I am done. How many variables are there? How many variables are there in this linear program? How many variables are there? As many as set of legal vectors. Okay. So, there is an algorithm by Kannan which shows integer linear program is FPT, fixed parameter tractable, parameterized by number of variables. And what is the running of times? Number of variables to the power number of variables times some poly, do not care about it. Okay. So, what is the running time of this algorithm will be? What is the running time of this algorithm will be? Does it depends on M anymore? No, it is an algorithm with running time. Okay, because of this, I can solve this ILP. Of course, this I can't teach you, I do not even know how to do this. It's going to be, what is the number of variables? Is like q to the power q and some polynomial factor, right. So, this is an FPT algorithm in number of legal vectors. Okay, excellent, right. Okay, so now we are ready to make this algorithm. Is it fun? Okay. So, first I had an XP algorithm because it was running time m to the power some legal vector, but now I have made an FPT algorithm because it is just FPT in the number of legal vectors. Before it was an XP algorithm, m to the power some function of legal vectors, right. Okay. But now the biggest problem is who gives me the control over k? You understand? Why? K could be very, very bad. Okay. I am going to bound k now. Okay. Is that fine? So, legal vectors done. The problem is who gives you control over k. So, you could do this. So, this kind of algorithm, right. So, we were looking for an 1 plus epsilon algorithm, right. We wanted to make an algorithm with approximation ratio. What was our goal? Our goal was to make an algorithm okay. So my goal was to design an approximation algorithm with ratio 1 plus epsilon times opt. This was my goal. I'm very far away from my goal at this point of time, but I'm almost there, okay. 1 plus epsilon times opt, okay. This was my goal, but there are two kinds of running time you can make. An algorithm with running time m to the power function of epsilon, this is called polynomial time approximation scheme, or you can make f of epsilon times m power big of 1, this is called efficient polynomial time approximation schemes, okay. So what we are going to make, so I'm going to show to you is that k is like some function of epsilon. If I show that k is nothing but function of epsilon, then what is the running time of this algorithm? If k is my function of epsilon, then what will be this algorithm? M to the power s is like some function of epsilon, then that's like a p task. But look at the second algorithm that I made. What is this? This is like some function of epsilon times some. So this is an FPT, so this is nothing but efficient polynomial time approximation schemes, okay. So this is EP task and this will give us P task. So what is EP task? Is nothing but an FPT algorithm parameterized by 1 over epsilon. And what is P task? Is an XP algorithm parameterized by 1 over epsilon. Okay, so how? How? This is easy, trivial. Okay, but anyway, our goal was 1 by 10, right? Our goal was n by 10, okay? So we know, so let's remember, P1, P2, Pn is opt by 10. This is all we know, right? This is the setting we are in. I'm only trying to make 1 plus 1 by 10 algorithm, okay? So if I show that the number of types k is like some g of 10, I'm happy, no? If I show k is g of 10, then I'm happy. And then all are done. Because then I have to make a pure polynomial time algorithm, which I made, f of g of 10, and I'm done. Okay. So now let's see. Okay. What do you think should we make? Okay. So let's start. Everybody is greater than equal to opt by 10, okay? 2 opt by 10, 3 opt by 10, 4 opt by 10, and opt. Is that fine? Fine grained buckets. Which jobs will go here? Right? So imagine that I like include this but exclude this, like it's an open interval. All the jobs will go here, some jobs will go here, some jobs will go here, some jobs will go here, and some jobs will go here. Is that fine? Is that fine? Okay. Now, what is the cost of the solution currently? Look at the bad bucket. Look at the bad bucket. Now, and what I'm going to tell is that for every guy, so if I have job here, no, I say your processing time is no more this. Your processing time is your boundary. You go and everybody's processing time is this. Is that fine? Everyone. So I change everybody. So all the jobs that is going to fall in this bucket, what is its processing time from now onwards? 2 opt by 10. If anything falls here, what is its processing time? 3 opt by 10. Whatever it falls here, what is its processing time? 4 opt by 10, and so on and so forth. Is that fine? Right? Okay. So now look at the worst bucket. Look at the bucket which gave us opt. how much it will give us now. This guy, whatever it is, how much did you add? How much did you add? Suppose there are 10 of them, and every time you were here, you added opt by 10, right? Opt by 10, opt by 10, opt by 10. So this is bad, no? How much it be? What is the current? You understand what I'm saying? Look at the processing time of the machine which is the largest. So it is P1, say P3, P5, P7, which is equal to opt. Now let's look at P1 prime, P3 prime, P5 prime, and P7 with the mapping. How much it has become? Everybody would have increased by how much? Opt by 10, no? Opt by 10. So it is if all of them were opt, 10 times opt by 10. 2 opt. This I did not want. Okay. Maybe I need some more fine-grained bucketing. You understand? Okay. But imagine that everybody increased not by opt by 10, by opt by 100. Then what happens? If everybody, I only increased by opt by 100. So P1 prime is opt by 100. Opt by 100. So 10 times will be opt by 100. That's great, no? Okay. So this is a bad bucketing. Okay. So suppose this is my smallest, and x is greater than or equal to opt by 10. Okay. I want to make like x plus opt by 100. Next bucket is x plus 2 times opt by 100, so on and so on. I can also do this, no? I can do this, right? Right. But now tell me, and I map again like this, how much it increased by? Opt by 100, no? So everybody has opt by 10. So they increase by how much? So now optimum in this increased by how much? Opt plus opt by 100. But how many different items we have? 100. Solve problem in optimum time, no? What will you get a solution? You will get a solution, if you map back, it is at most opt plus opt by 100, opt by 10. Hey, 1 plus 1 by 10 approximation, you are done. No, you don't get it? You understood or you do not understand? So I am creating a new problem, right? Jobs remains the same. Jobs remains. Now processing time. I say, which bucket are you falling, man? He says, oh, I'm here. So each bucket, each processing time is element of, now I say, what is Pi prime? Is nothing but some x plus I by opt by 100. This is what it is, your processing time. What is your processing time? Is if you are here, next one, right? So what is the property of each processing time? Each Pi prime is greater than or equal to Pi, but it is Pi plus opt by 100. Is that fine? Right? Because if you are falling in this bucket, I put you here. So new Pi prime is opt by 100. But how many distinct Pi's? How many distinct Pi's? Is 100. So I said, with this modified instance, solve my problem. Right? Because still, okay, so if I solve this modified problem, in polynomial time, I can get a solution with how much cost? I will get a solution with cost 1 plus 1 by 100 of opt with this. So if I delete this Pi prime, I can only get down, no? So this is what you do. So this is how you can reduce the number of types by making this bucketing trick. Okay, of course, I need to make this all formal and everything, but this is what you do to this. So now if I was looking for 1 plus epsilon algorithm, if I looking for 1 plus epsilon algorithm, if I was looking for 1 plus epsilon algorithm, I know that this should be epsilon times opt, right? Right, a Pn is at least epsilon times opt. I will make buckets, which is some function of epsilon, do this, run my algorithm, and I will be done. But there are several things. So this is an algorithm which, if the buckets, so I knew two things in this algorithm. I knew what opt was, and I assumed that every item is big. Who told us this? There are two things. You understand the assumption? First, I assume I knew opt. I mean, like, what is this? This is very bad. Okay. And secondly, I also assumed that somehow there is no small, because I have not given you that future algorithm. How do you know that handles everything? You understand?
Sorry, what is this? Which future algorithm?
Huh?
Which future algorithm? You just now said.
Future algorithm.
No, you just now said.
I didn't make any future algorithm, but I said I tried to prove that induction, right? Oh, if the last item is less than epsilon by 100, oh, I'm done. How do you know you are done? Right? I have never made that algorithm.
So the main point is that the objects need not be all homogeneous, like big size. They could be small, big, small.
No. I have assumed that every item is at least epsilon times opt.
Yes.
I don't know opt, and how do I know that every item is more than epsilon times opt? I don't know either of the.
You're saying that need not happen. Like
Of course, it will not happen. How do I handle this? Okay, so now let me make my. So this is my big bucket algorithm. This is what? Big bucket algorithm.
Okay, just one question. This further refining this bucket, so you saw that opt by 10 size buckets was not enough. So you further split that 10 size
Yeah,
bucket.
whatever I
into
want.
10, 10, yes. So I can then, why can't I potentially push this idea, take vanishingly small bucket?
Yeah, then the vanishingly small running time will increase and kill you.
So that's the
Yeah. So more you refine, more you pay in the running time. Okay. So you at least understood that how big item algorithm. I'm not doing any computation at this point. It's dirty, but I have told all the ideas. Okay. Someone who is taking the notes will have to do all this dirty job. Huh? I don't know who is taking. Who? You are going for trek, no? I attended Monday. Okay. So several things that we need to handle at this point of time. Okay. Okay. So now I'm going to try the algorithm first of all. Okay. So now I'm going to write down first algorithm, and then I'll write the second algorithm if required. Okay. So first of all, let me make an algorithm. I know opt, and then I will tell you how to handle when I don't know opt. Okay. So first, we know opt. So this is an assumption I'm making still. Okay, but I could have buckets. So if I know opt, not buckets, that's algorithm done. I know what is my small buckets and what is my big buckets are. Small buckets, not buckets. Small jobs, big jobs. Okay, big jobs. Okay. So what I will do on this algorithm, okay. So I know this. Okay. So here's my lemma, which says that, which will tell us that if we do first, let's do the big job, and then assign a small job using my greedy algorithm. You're great. You understand my point? So let me formalize. I wrote it down as a lemma. I'll tell you precisely what statement I would like to do. Otherwise, okay. So this is a precise statement. Okay. So suppose, okay, suppose we have an assignment. We have an assignment sigma b from of the big jobs. Okay, big jobs with make span alg b. So the largest amount of, like, how much it is. This is alg b. Then running the list scheduling algorithm. I am not even asking you to run this greedy algorithm. Then run the list scheduling algorithm on the jobs in S, small jobs. Okay. after having assigned Is that fine? So, what I am saying to you, so let us suppose we have an assignment for B to M of big jobs with their max span, the largest, like the longest time it takes on any job is alg B. Then after this, then I am going to run a list scheduling algorithm on the jobs in S after having assigned. So, first what will I do? What my algorithm does is the following. Okay. So, what my algorithm does, it says, okay, first let us take these big buckets and let us assign them on the machine, okay, using this sigma B. Like it tells us which big jobs will go to which. I did this first. Now, in arbitrary order, I take the small jobs and assign it to the machine which has the least load. That's a first, like in any order. Then I take care of small jobs, small, that's it. Then what I am guaranteeing you, then this sigma, what is its max span? Either it is alg of B or it is 1 plus epsilon times opt. Okay? Why? Are we done? This is easy to prove. Okay. Proof. Now look at this, right? Let L be the job that finishes last. That is what I always care, no? Finishes last. Okay? If J is in B, what can you say? It means after I did all this, red are anywhere here. It's a big of the blue.
Do you mean L is in B?
L. Yeah.
You meant last job is in B.
If L is in the B, what is the meaning of that? Right? So, I first scheduled the blue job and then I schedule this red job, and I am saying the last job that finishes is blue still. So, in this case, what does it implies?
B is that
Then it replies alg is less than equal to alg of B. Okay. Otherwise, what is the last job? Last job is this. Then what does it say? If you recall my analysis, what does it say? It is opt plus 1 minus 1 by m of PL, right? That is what I always say, that because it is about any ordering or anything, right? So, this is opt plus 1 minus 1 by m, and PL is a small job. So, it is epsilon times opt. So, this is 1 plus epsilon times opt, it is minus. Is that fine? So, I am done. This is what it is. Okay. So, now you understand. So, if I can show that the big items is 1 plus epsilon approximation, then I am done. If big is also 1 plus epsilon times opt, then I am done. So, this is why I can forget my small jobs, because small jobs I first do the big jobs and then the small jobs just fill them whichever you can fill with list, and then you are still happy. So, now we can forget small jobs. Okay. So, we can just concentrate on the big job. Okay. But to do the big job and small job, it requires opt, right? Because my algorithm is first do something on the big, but to do big I need opt. Okay. I'll come. So this is a trick 2. Okay. So what did we learned several tricks today. One, we learned bucket tricks to reduce the types. Then if the types are small, I can use ILP. That was another idea. And final idea is how do I know opt? How do I know opt? Do I know opt? At least do I know estimate on opt? Opt is greater than equal to L, which was max of L1, comma L2, where L1 was max of PIs and L2 was summation PIs divided by M. Do you agree? And what did we also learn by that algorithm? Opt is upper bounded by 2L. Is that fine? We also knew that opt is upper bounded by 2L. Right? Okay. So let's pretend. So what will I do? I said now I will start to pretend that I know opt. How? I will say again bucket, bucket, bucket. Okay. So I say okay, I have actually no idea what your opt is, but like let me pretend is opt equal to L. I can pretend that opt is equal to L. Run your algorithm, right? Using this as an opt. So either I get an 1 plus epsilon opt algorithm for this or I am dead. Okay, fine. If I am dead, then what will say? Okay, let me see. It means definitely this is not an opt. Okay. Okay, so maybe opt is 1 plus some delta times L. Delta I have to fix. Okay, let's try this. Succeed? Then what happens? Then if I succeed, look at the first time I succeed. So when I succeed at say 1 plus delta times j. No, I don't want to do this. Okay, I want to say this is opt 1, opt 2, opt j is nothing but j minus 1 delta times L. I'm just increasing, up to me, right? So I succeeded here. So what I knew that opt is at least greater than equal to 1 plus, so suppose I succeed at j plus 1. So I know.
How do you know you succeed? You have not overshot the time.
I'm running this algorithm with this, pretending this is an opt.
For each of them you get some answer.
Yeah.
How do you know what is the notion of failure here?
Failure. If my make span is more than 1 plus epsilon times my current estimate. If my current estimate is more, like if my current estimate would have been correct, if my current estimate would have been correct, I will not fail, no? If my current estimate would be correct, oh, this is actually opt, I will never fail.
So I keep a timer and count up until this?
No, I don't keep a timer.
No, if it goes on beyond that, then
No, why? No, I have a fixed algorithm. It is not, it's an approximation factor, it's not running time.
Your notion that is that an analysis which is this notion of failure, isn't that something that I will be because I have to keep on changing?
Yeah, but I run my, so this is just a loop, some delta times.
Sure, but I'm saying that the detection that this is this guess. This
No, I will just run my whole algorithm. My algorithm runs in poly time, it returns me some solution. I look at the quality.
You run your algorithm each time with that estimate of opt.
Yes.
So when you are at say estimate 2, you know you kind of check right that within this many time steps the algorithm should have ended if my estimate was correct.
No, I don't need to because the estimates are just too little. Like I'm only, look, I failed now, right? Whenever, like I failed now.
That's your failing condition.
Look, I started with here, no? I started with here. This is definitely opt is greater than equal to L, no?
Yes.
I should not, like, if I fail, I will fail in whatever I fail. This is perfect. My algorithm will stop at this point of time.
I do not. Then why am I trying with opt 2 then?
Because my approximation ratio is not 1 plus this.
So yes, you fail at the opt 1 step.
Yeah, what it means? It just means,
What is that notion of, and how will the algorithm?
suppose my opt,
So I'm asking when does the algorithm move on to the next estimate? Like
yeah, so imagine, I'm supposed to get algorithm with ratio 1 plus epsilon times L. This is what I'm allowed. quality. It says, nah, I made my algorithm, I did whatever you asked me, but make span alg is actually 1 plus epsilon times L. Then I know this L is wrong. Because if my correct L would have been there, my algorithm will succeed with 1 plus epsilon. Okay, so then this is wrong. Okay, then I say next one. Try next one. I will, up to 2L I will succeed somewhere, no? Because that is an upper bound, right? So the first time I succeed, why I succeeded? Then I know, first time I succeed at j plus 1. Then I know that actually opt is strictly greater than 1 plus j times n plus j times delta times L and less than equal to 1 plus j plus 1 times delta times L. This is what it is. And what I have returned, yes, this is what,
That's its sandwich between them.
exactly. But what I am returning? I am returning a solution which is opt tilde, which is less than equal to 1 plus this, 1 plus this, right? It is opt tilde is 1 plus epsilon of 1 plus j plus 1 times delta times L, right? So this is equal to 1 plus epsilon times 1 plus j plus 1 times delta, yeah, fine, times opt, because opt is greater than equal to L. Great. But now, so basically I will run this algorithm with this not epsilon, but I will run this algorithm with some epsilon prime. Okay, so I say, you have given me some epsilon prime, epsilon prime. All I care about is this should be less than equal to 1 plus real epsilon times opt. I will choose epsilon prime, j, delta, everything is in my hand, I choose. That's it. So this is how I can take care of even knowing opt. I can cheat, right? So I start with L, start with 2L, little, I increase, I say, hey, tell me. So like I'm doing, I could also do a binary search for all that I care, right? I said L, okay, fine. Maybe 3L by 2 less than this. I mean, I can do some binary search and reduce this number of steps, but like, let's do tiny steps. So I do this, I do this, I do this, I do this. At some estimate, I pass. I have my algorithm. Okay? Then I'm done. You understood the algorithm, right? So there were several steps, okay? So, but these are like, these steps are like this is not something which is accustomed to load balancing. This is like used everywhere, okay? That's, these two tricks are for almost, you do knapsack, you will do the same thing. Partition, you will do the same thing. Subset sum, you do the same thing, okay? Second was type reduction, okay? Second was type reduction, making the buckets. That is also, when you are playing with numbers of numbers, you do all the time, okay? So this is not something which is, we are doing it for the first time in our lives, right? We do it all the time, you understand? And, okay, you understand? But there are several questions that you can ask. Why the buckets, number of buckets is a function of epsilon? That you should ask yourself a question, right? So the way we are making bucket, so how do you make buckets, right? So first of all, this tells us that this is a stupid trick that tells us that we don't have to worry about opt. We can pretend that we know opt, because with little bit of more extra factor, we can deal with it. So then after this, we know that we are only dealing with an algorithm for epsilon opt. Now I try to make a bucket. What is a bucket? So this is why something we have to understand very, very properly. That this is important, that they are greater than or equal to epsilon times opt. Otherwise, your buckets will be pathetic. It could be log n. Imagine that I have 1. So imagine that I have numbers from 1 to n. 1 to n numbers. Okay, I have n numbers and I want to do bucket, right? If I make a bucket of 2, like 2 power 0 to 2 power 1 to 2 power 2, 2 power 3, 2 power log n, right? So how many buckets are there? Log n buckets are there. I cannot reduce this, right? But here I am going to assume the fact, but imagine if I ask you, how many buckets you have, how many buckets can you make if I told you every number every number is greater than equal to epsilon times n, then how many buckets will you make? Okay. Is the first bucket valid? This 2 power 0, 2 power 1 bucket valid?
You start from the epsilon n.
No. I start with, is this bucket valid? No, right? The first bucket, which will be non-empty, right? It will be much, much later here, right? So how many buckets are left here? You understand? So what I know, I am starting from epsilon n and I need to go to n, right? I am starting at epsilon n and I need to go to n. So next time what happens? You,
The first bucket that you put some material
so where is this bucket? Where is this number? Please tell me, where is this number?
power log n bucket. Log epsilon n bucket.
Log epsilon n bucket probably, right? What is this? Log
Epsilon n.
right? And to log n, you can see that this is the only function of epsilon, okay? So, or more importantly, what are we trying to understand, okay? So what we are trying to do is the following. Okay. So after I have done all this trick, Pj is any new number. Pj is epsilon times opt and 1 plus epsilon times opt. Okay? And if I am making a bucket of size 1 plus epsilon, right? So basically I can think of my smallest bucket being 1 plus epsilon times x, and starting from this is my smallest bucket, I take r more steps, 1 plus epsilon times x, 1 by, so my buckets are going to be 1 by epsilon times x, 1 plus epsilon x plus 1, this is one bucket, 1 plus epsilon times x plus 2, this bucket, till I reach 1 plus epsilon times x plus r, where x plus r is this value, the largest value of any Pj, right? So what is this? So what are we getting? We are getting 1 plus epsilon times, so we want to reach from here, right? Right? How many, so what I want, x plus 1 plus epsilon to the power x plus r should be less than equal to how much? 1 plus epsilon times opt, right? Okay. Now what is this? It is 1 plus epsilon times x times 1 plus epsilon times r is less than equal to 1 plus epsilon times opt. Is that fine? But what is 1 plus epsilon times x? Is epsilon times opt, right? So this implies epsilon times opt is 1 plus epsilon times r is less than equal to 1 plus epsilon times opt. Opt gets cancelled. Now, so r is what? From here, what is r? If I do this computation, so one second. So 1 plus epsilon times r should be less than equal to 1 plus epsilon by epsilon. Is that fine? So what is this? R is less than equal to log 1 plus epsilon by epsilon. Is that fine? I have taken with base 1 plus epsilon. That's it. So r is less than equal to this, right? So how many buckets do we have? We do have buckets as a function of epsilon. Great. That's all that I cared, right? So this is why I must start from large enough, otherwise you will start to get a log n, right? But if you are starting, so it's like, it's very simple, no? If I start at much ahead, how many, if I start at n by 4, how many steps do I need if I double this to reach n? 2 steps only, no? This is exactly what this. So you will need some function of epsilon step to reach that much. Okay? So this is why the number of buckets becomes small. So once the bucket becomes small, we can do like so. Then I have already shown that if the buckets are small, my opt only increases by a little bit. You try to find a solution with respect to that, and you just scale it back. Okay? And okay.
Imagine a situation where we don't have a large lower bound on, like within epsilon opt, right? That lower bound is actually small, but we know that there are lots of values higher up that don't exist.
Huh?
Can't I have discontinuous buckets?
You could have. It's just that it doesn't depend on the. It all depends on how many distinct buckets you are making. That's it. Yeah, this is why I wrote k, right? No, it does not have to be. Okay. Is that fine? So who is taking these notes? Who's taking these notes? You. Okay. You come, I will give you algorithm. Okay. But this algorithm has running time. If you notice, this algorithm will running time will have roughly 2 power O tilde 1 over epsilon, like some basically O 1 over epsilon log 1 over epsilon to the power some constant t. So this is the running time of this algorithm, but there is we can also do some hard work to get this 2 off, but like that's for different thing. Okay, that's all.